the things we were talking about before the midterm was the particle on a ring. And we said we could talk about the particle in a ring in a relatively simple way by recognizing that we've got negative h bar squared over 2I d by d phi squared operating on some function psi of phi equals to e psi of phi. This was the Schrodinger equation we set up for the particle in a 1D ring. Sorry, in a ring. It's a two-dimensional, and this is kind of one of the interesting things and why the reason we switched our coordinates, right? If we did this in x, y, this would actually be a 2D problem. We'd have to have a d by dx and a d by dy. Since we switched to phi, this conveniently makes it so we've got answers that are just in terms of one dimension. We said we can, looking at this and saying, oh, this has the same functionality kind of setup as the particle in a box. We said that we could guess that the phi functions are going to be something like e to the I m phi, where I'm going to go ahead and give that a subscript L. Now, calling this m sub L doesn't make sense until we go to multidimensional systems. And then the reason that we're calling that m sub L will make more sense there. It is also related to that m sub L from general chemistry that we all remember when we did our quantum numbers. And we're actually going to come up with a mathematical explanation for where those numbers come from and what they relate to. So we had that. Then we also had our energy equation equal to ml squared h bar squared divided by 2I. Remembering that I is that moment of inertia, mr squared. So this is essentially the particle in a ring, right? And we've got the essential parts that we've done for all of our problems. We set up a Hamiltonian, making sure we take into account any potential energies or anything that's there. We solve for the wave functions of the energies. And usually in doing that, we end up with some counting number. I should also say m sub L is equal to negative some number, and this is just some number. I don't want to call it n because I don't want you to think that it's related to the n value. It's just negative number all the way up to negative 2, negative 1, 0, 1, 2, all the way up to positive whatever number. Right? And the part that was interesting to me, and it took me a bit to be like, oh yeah, right. The fact that we can have zero energy, right? That should have bothered all of us. Right? When we did the particle in a box, we said, oh, we can't have zero energy and it has to be equal to 1. Because if we have zero energy, we exactly know the momentum and we exactly know the position. And due to our wave function relationship between position and momentum, the uncertainty principle says we shouldn't be able to know both of those things. But we have to keep in mind, when we converted this down, we saw the same thing in harmonic oscillator. Right? We had no zero, like the energy was never zero. The reason that we have it in this case is because we essentially have an artificial restriction on the problem, right? Someplace in here I said, oh, the radius is a constant. We exactly know the radius. And if we exactly know the radius, if I'm allowed to just say it's a constant, then we get a problem that doesn't really make physical sense, but allows us to do a simple like rotational solution. Really, that radius of the ring should be fluctuating a little bit. And that's where this 0-point energy, the fact that there's some uncertainty, would come back in. We don't get that until we go to more dimensions, until we look at a rigid rotor in 3 dimensions to get that restriction back, because we have to take that R component into account. We can't just have a fixed R. We're artificially limiting our system. So this means we're going to launch into 3-dimensional rotation particles. And when we do that, we're going to find that these answers that we have are going to be useful, but we're going to have to get a little bit more complicated, which is probably why I feel nervous today. So we have to know a couple things. our L vector, if we're doing classical mechanics, our L vector is going to be some R vector cross some momentum vector. Does that seem familiar? All right, we're going to get R cross P, and I could set this up in terms of the matrix. We're not really going to do this too often, but I can have my I, my J, and my K vectors, and then I can have my X, my Y, and my Z, and I can have my PX, my PY, and my PZ. And if I wanted to switch this from doing classical mechanics to quantum mechanics, I would change all of these things rather than being vectors. These would be three-dimensional operators. And this is going to allow me to define, instead of just having one rotational direction, it's going to allow me to define many rotational directions. I'm essentially going to be able to say my Lx hat operator is going to be ypz minus zpy. My Ly operator is going to be negative, so it's going to be the z hat px minus x hat pz. And my Lz operator is going to be xy, x hat py, minus y hat px. And essentially, this gives me this idea of rotation in three-dimensional space, looking at the position and the momentum, and kind of seeing how those things are connected if I'm looking at the z component, the y component, or the x component. And the first thing that we should say is, oh, wouldn't this be better if we did it in spherical coordinate systems? The answer is kind of yes. So just as a reminder, we can write down our spherical coordinates. X is equal to r, I gotta get this right. R sine theta, cosine phi. Y is equal to r sine theta sine phi. And z is equal to r cosine theta. And we used this last class to say, oh, particle in a ring makes sense if we remember that our theta, if we have our three-dimensional coordinate system, theta is going to be our tilt angle down from the z-axis, and our phi is going to be that rotational angle in the xy plane. I don't know if you can tell with my poor three-dimensional picture. Essentially, theta is the one that tips away from the z, and phi is the rotation in the xy plane. Theta is going to be limited from 0 to pi, whereas phi is going to be from 0 all the way around to 2 pi. Just as a reminder. So we can look at this and say, okay, so if we want to just be in the xy plane, we set our theta to pi over 2. Is that right? Theta goes to pi over 2. Sine theta, sine phi. The xy components kind of are going to disappear, and we're just going to end up with an Lz component in that case when we plug everything in. Now, when we look at this in terms of these operators, these different directional motions, we get something a little bit ugly for x and y, which is the reason we usually talk about this in the rigid rotor case, why we talk about the Lz component. Because it turns out the Lz part comes out quite simple. The Lx operator, and you're never going to need to use this one, so feel free to skip writing this down, but I do want to show you. The Lx operator in spherical coordinates would be negative IH bar sine phi minus cotangent theta cosine phi d by d phi. I forgot a d by d theta. D by d theta. And this is now curly d because these are, since we're doing multiple dimensions, we're now doing partial derivatives. Ly has a similar form. Negative I h bar cosine phi d by d theta minus cotangent theta sine phi d by d phi. And the reason we like LZ and the reason we talk about the LZ operator is because when we do this conversion for LZ, we're going to get just negative I h bar d by d phi. The LZ one works out really nice. Now, it's fair to say that this is somewhat arbitrary. How do we pick what direction is Z? Well, for us, whichever direction we pick for Z is going to be the simplest direction for doing calculations on it. So Z is going to be the kind of direction that we want to pay attention to. You'll also notice that with this rearrangement, I can really look at this problem that we did for the particle in a ring, and I can say that this is, for a particle in a ring, ooh, that's not as pretty as I want to write, LZ hat squared divided by 2I psi of phi equals E psi of phi. So using this definition in three-dimensional space, I can see that the problem we solved is actually directly related to this idea of three-dimensional space, where again, if you set theta equal to pi over 2, both of these terms are going to collapse down and stop existing. And since theta is going to be a constant, these terms are also going to stop existing. We're not going to have any Lx or Ly rotation if we lock that theta value. But now what we want to start doing is we want to start letting that theta value vary along with that phi value, and we want to see how this rotation happens along this here. We're still going to keep R locked for now. We're going to let R be constant. We'll start changing R by the end of this class or the start of next class. So we're really just going to see if I have a particle not constrained to a ring, but constrained to a sphere, constrained just to the surface of some orb. How does that behavior get communicated through all of this? So if we're going to say, okay, this problem where we just had phi, we now want to have theta and phi, clearly this is going to be a little bit more complicated than what we had before. And there's a couple ways that we can look at it in order to simplify it. The first thing that we're going to introduce is the del squared operator. Del squared is going to be different it's essentially what we've already been doing, but generic for any coordinate system we want to use. If we're in the xyz coordinate system, this is d by dx squared plus d by dy squared plus d by dz squared. If we're in the xyz coordinate system, it works out pretty simply. We now want to say, okay, well, I want to look at this, and the reason we like this before we look at it in spherical coordinates is because this allows us to write our kinetic energy generically as negative h bar squared over 2m del squared. So this is going to be three-dimensional for any coordinate system that we want to do. And that gives us a generic way to write down our kinetic energy. We can start playing the games that got us here originally. We can start saying, well, what if we wanted to just keep it in one dimension? If we kept it in one dimension, say our dx, we'd ignore the y and z, and we'd get back particle in a box. If we say, okay, let's do 2 dimensions, we could get our dx dy, we'd be getting to particle in a ring. Right? So we can get back to the same problems we've already done by putting restrictions on this type of idea. Or we can broaden it and start looking at new problems as well. And that's, of course, what we're going to do. So if we look at, oh, I'm going to need this whole bottom to this part. If we look at del squared in spherical coordinates, this is the full three-dimensional del squared. And we're going to simplify some of these parts for the ring. You're going to see that there's going to be a radial part. We're going to have Okay, there we go. I like this one better. 1 over r squared d by dr, r squared d by dr, plus 1 over r squared sine theta d by d theta sine theta d by d theta, plus 1 over r squared sine theta squared d by d phi squared. That is del squared in spherical coordinates. And when we originally look at this, we're like, oh my god, we just made such a bigger mess than x, y, z. But keep in mind, the differential we write down is not really, making that simple is not the thing that makes us happy. Getting a differential equation that's easy to solve is what makes us happy. And we're going to be able to use separation of variables on this. You notice if I can bring out this r squared, I'm going to have something that just depends on theta and phi, and something that just depends on r. So I'm going to be able to split this out. And that's what we do when we're looking at the rigid rotor. We say r is a constant still, right? Not necessarily true in the atomic world, but r is a constant, so we're going to ignore all of these d by drs because that's all going to be 0. And we're just going to focus in on the rotational parts, the thetas and phi's parts. And you'll notice we've already got some like LZ squared thing here, right? We've already got something that's closely related to LZ squared inside of this. So it's again not going to be that difficult to do separation of variables, solve the phi part where we already have solutions, and then come and solve the theta part. And I say not that difficult for mathematicians to do. For us, we can look at some of the parallelism that exists between the Hermite polynomials, those things we got for the harmonic oscillator, and the solutions we get for this differential equation. But we're really not going to be doing, just like we didn't do the solutions for the Hermite polynomials by doing a power series expansion and blah, 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 we're not going to be doing that for these either. We're going to be looking at the wave functions that are the solutions to this and figuring out how that gives us interesting information about the physical system. So let's go ahead and think about that. So, okay. I'm going to go ahead and erase all this. We'll need those answers again, so hopefully you have them written down in your notes. These will, am I going to want to write those? Am I going to want those again? Nah, we'll get rid of those for now. There's something we're going to do at the end of class where we're going to look at those again, but for now we'll get rid of them. Let's see. If r is constant, we're going to define, we're going to do a little bit of a change. We're going to just look at this sine theta, d by d theta part to the d by d phi part. And that is such a common set of differentials that it actually gets its own name, its own little symbol. It's a capital lambda. It's a bit too much for a lambda. Capital lambda squared is going to be just this part here with the r squared moved out. That's going to be capital lambda. We're going to get a 1 over sine theta d by d theta sine theta d by d theta. Notice we're going to have to apply, that's not a theta. We're going to have to apply the chain rule here. So even though we didn't do a lot of chain rule on the midterm, chain rule is going to come back. And in this situation where we've got our constant radius, we can essentially say that this thing, make sure, we can, any questions yet? Okay. I don't know why I'm feeling very nervous about doing all of this today. I feel nervous today. So, question, yes?
Should that be theta?
Which one?
In the last one.
No, that should be phi squared. So it should be sine theta d by d theta sine theta, and then 1 over sine squared theta d by d phi squared. And that defines this operator. So in this situation, right, that's where I am. Okay. So in this situation, we can essentially set up a problem. What do I want to set up? There we go. Where our Hamiltonian is going to be a negative h bar squared on 2m lambda squared. And that should be a lambda squared operator as well. Just looks funny with the double P. And in recognizing the kind of parallels from the other problems we've done, we can also recognize that this is going to be some sort of momentum term, right? The same thing we saw when we did particle in a box, same thing we saw when we did particle in a ring. And we can collapse this down, and we can say that this is also related to L hat squared over 2m. So we can look at this in terms of just the differentials, or if we wanted to make a good quantum mechanical operator, something that has that Hermitian property, we would be looking at this in terms of some momentum squared operator that's going to have an IH bar up front, and when we square that, that's where the negative H bar squared comes from. Question?
Are we leaving out 1 over r squared because of the fixed?
Yeah, so that's just a constant. I took that out. We can say that this is like divided by r squared, right? There's a constant in there as well. But for now, we're kind of ignoring that constant. It's going to be very important in the future, but right now we're just like, it's a constant. So, at this point, this is the part where it gets a little bit tricky, right? So at this point, if we wanted to solve this, if we wanted to have L squared over, oh, you know what we do? Sorry. We do want to keep that r squared there, the r squared there, and we're going to switch this to an I. Important thing. So we don't want to ignore it. It's a constant, but we still want to bring it along so we get moment of inertia like we did for our other rotational problem. So if you missed that in your notes, this is eta divided by r squared because we do want to have that, we still want to have that r squared term that's out front there. And then we want to bring that along so we get L squared over 2I. Thank you. I almost messed that up. Actually, it's just here that we want that divided by r squared. We don't want to ignore this for the del. So, to be clear, the del has the r squared term in it. We want to be doing the kinetic energy as negative h bar squared over 2m del squared. We're setting r to be a constant so we can ignore this first term, but we still have the 1 over r squared. When we bring it over into the Hamiltonian, we're going to have essentially eta divided by r squared. So eta doesn't have the the lambda squared doesn't have the r squared in it, but when we do our Hamiltonian, since we want it to be for del, we definitely need that r squared to come along. That's why I messed up, because I'm jumping around. So bringing that r squared along in the Hamiltonian, we're essentially just going to do the same combination we did before, where we've got mr squared to give us an I. And this is really nice, and this looks much nicer, right? Because now this looks just like the rotational problem we did before. We've got some angular momentum squared operator. We've got an I for our moment of inertia on bottom. And we can start looking at how we solve that. we're going to be looking at situations where we just have theta and phi. That r is a constant, so we don't need to worry about that. And don't write this down quite yet, because there's a convention that exists. And the convention is, again, because people already know what the answers are going to look like. The convention is when we have these functions in terms of thetas and phis, instead of calling it psi, we're actually going to call it capital Y. And this is convention because other people solved this before, and they were like, we're going to call it Y. So that's our theta and phi part that we're going to be looking at. Now, this is the part where it gets kind of tricky, and we can start kind of imagining different ways that we could go about this. You know, we can start by recognizing the fact that we can do some separation of variables. You know, we can rearrange this to some degree. We can bring this sine theta out. We can multiply everything by sine theta and just get a d by d phi part. And if we write this all out, it's a bit of a mess, but we can do this part where we're going to have one thing, we're going to have another thing. And when we do that, actually, I'm going to go ahead and do, yeah, I'm going to do that. So if we multiply through by a sine theta, we're going to get sine theta, d by d theta, sine theta, d by d theta, y of theta phi, with a 1 negative h bar squared over 2I on the outside, operating on that, plus d by d phi squared, operating on y of theta and phi. And that's all going to be equal to sine squared theta e y theta phi. What we can essentially recognize at this point with another rearrangement is we can bring the sine theta term over here and the d by d phi term over here, and we essentially get one part that only depends on phi, and we get another part, which is going to be this with this, that only depends on theta. That's going to allow us to essentially set up some parameters for solving this. We're going to say that when we did this before, hopefully you remember, and I know this was a bit of consternation, but when we did this for our two-dimensional box and we had our x part and a y part, we said the varying part is going to be equal to one constant, the other varying part is equal to another constant, so I can add the equations back together and get the same equation. So this part's going to be equal to the positive version of the constant, this part's going to be equal to the negative version of the constant, so the constant disappears. We're going to call that constant L. So this is the part where when we look at this part, that's only phi, we should, oh, question, yes?
Why is the negative before on that not squared?
Oh, that should be squared, because I forgot to square it. Thank you. Other question?
What happened to the 1 over sine 2?
So when we multiplied through by sine squared, so to get rid of this, oh, where'd that 1 go? To get rid of this sine squared, we multiplied through by, actually, I guess it's easier to see up here. To get rid of this sine squared, we multiplied through by sine squared. So we had sine squared theta divided by sine theta. That canceled out one of them. That's also why we end up with the sine squared theta on this energy term. So the energy is going to ride along with the thetas, and that's going to give us our L constant. And then the phi part is going to essentially be restricted, and our solutions here are going to be restricted by that L part, so that this equation remains true. And that's where we say, okay, this is going to have some solutions that look like the particle in a ring that had a constant m, but in this situation, that constant m is also going to be restricted by this constant L. the energy part we solve for. And that's where you get the m sub L, is because when you're doing it in 2 dimensions, this phi part has to be related to this theta part as well. And that's where, if you, do you remember the restrictions L versus m sub L from Gen Chem? We'll look at them in a minute, but those restrictions come out of this relationship. The phi part, we can pretty easily kind of say that's going to be some exponential term, just like we already saw. This part's a little bit, the theta part's a little bit more tricky to deal with. There are quite a few tricks that we can look at for how we guess about this, but really, you know, we're going to get something that kind of resembles, slightly resembles, what we saw for the harmonic oscillator, right? I'm going to have some like sine theta d by d theta part, and then some sine squared theta part. So I've got like an x, I've got my d by dx, and then I've got an x squared like term. And for that reason, we should go through and do the same kind of like polynomial expansion that we never even talked about in class. I think I mentioned it, but you can do a whole process for solving differential equations. And if we wanted to put, you know, a couple weeks into getting good at solving differential equations, we could do that. But we're going to look at the answers. Yeah, that'll be a headache later. We can look at the answers to this and kind of see that similarity to what we saw in the harmonic oscillator. And again, because we're solving something that has similar functional forms, but now we've got sine thetas instead of x's. And we're also, because we're doing trig functions, we're going to be able to use things like sine theta squared plus cosine theta squared equals 1. And we're going to be able to use things like the offset, like, cosine theta equals sine theta plus pi over 2. Sine theta plus pi over 2. Like, they're just offset by a pi over 2. So we're going to be able to use those types of trig identities to make simplifications and extra kind of smaller answers. But they're still going to follow the same kind of idea. So I'm going to write down all of the y functions. And we're going to get some m sub l's due to that part. We're going to get some l's due to that part. And the l's and the m sub l's have to be related to each other since we're doing a separation of variables. So we represent this as L sub, so L comma m sub L in the subscript. Other books do it different ways. Some people put the L on the bottom and the m sub L on the top. Some people put the L, m sub L on bottom. Your textbook does it this way, so I'm going with that, even though it's not the way I learned it. So if we wanted to look at these, and again, these are things that would always be given to you if you need them. You would never actually have to write these. You would never have to remember these. If we did y0, comma 0, that's the L equals 0, m sub L equals 0. This would end up being the most symmetric case. We'd get a 1 over the square root. This is the normalized 1 over 4 square root 4 pi. Right, so this would essentially say it's just a constant, right? Your probability over the entire thing is just a constant. Then we could look at the y1, comma 0. And this would be 3 over 4 pi to the 1/2 cosine theta. Which the reason we get cosine thetas is, again, when we start doing this chain rule, making sure that things cancel out, cosine theta works out for this situation. It's going to be different when we go to you know, higher order solutions, but if we've got the 1,0 case where this phi part is kind of not participating, the way that the derivatives work out, and we could prove that. Oh, I should have made a worksheet that has to do all that. I made a much more difficult worksheet. We can look at the y 2, 0. Except for I just lost my page. And I'm hoping, the reason I'm writing these all down is because I'm hoping that you'll see the kind of pattern that we saw before. 5/16, pi to the 1/2, 3 cosine squared theta minus 1. And I'll write one more before we look for the pattern. 3 comma 0 is equal to 7/16 pi to the 1/2, 5 cosine cubed theta minus 3 cosine theta. Do me a favor. Someplace buried in your notes or on your equation sheet, you have the Hermite polynomials, the ones that were the harmonic oscillator solutions. It's definitely on your equations sheet for the given equations, wave functions and energies part. But you'll notice we've got something that's even, odd, just like we had before. We've got something that's like an x squared minus a constant, an x cubed minus an x. This is going to look very similar. It's not exactly the same, but it looks very similar to what we saw with the harmonic oscillator because the functional form of the differential equations are actually not that far off. Just like we never actually had to solve the differential equations for the harmonic oscillator, we will never actually solve the differential equations for the spherical harmonics. We're going to use them to look at interesting things. The catch is, because we've got this other value that we can think about, this phi part, bringing this phi part along, especially since it's going to have a functional form that's like an e to the im phi, that I phi is going to allow for extra terms to cancel out, and it's going to give us some extra functions, some different functions that we can look at. So we can also have y1 comma plus or minus 1. We can have a 0, a minus 1, a 0, and a 1. But it turns out the plus and minus 1s kind of have the same functional form. 3/8 pi to the 1/2 sine theta e to the plus or minus I phi. Right, and this e to the I phi part is what makes it so we can use the sine theta when we're looking at how everything cancels out. Again, this is an exercise we could spend a lot of time on. Right? If you think about the harmonic oscillators worksheet, we spent an entire class showing that those were eigenfunctions of the Hamiltonian, showing that they were orthogonal, showing that we could normalize them, showing that we could calculate the energies of them. You can imagine instead doing it with these functions and it taking a little bit longer and being a little bit more of a headache. We could do that. There are some homework problems that I think ask you to do that. But I think there's more interesting things that we can look at. I'm going to write down one more set of functions. And then we're not really going to, and then we'll talk about how we're going to use these. 1/2 sine theta cosine theta. Oh, no. Sine theta cosine theta e to the plus or minus I phi. Here are the nice things about this. These are the wave functions for a Hermitian operator. So we know that these functions should already be orthogonal to each other. We could show that, right? We can take any one of these functions, compare it to another function, do the integration over all of the allowed parameter space. I'm going to set that one up because we've got to make sure that we understand how we're parameterizing these integrals. So let's imagine that we wanted to show that two of these functions are orthogonal to each other. Why do I curse myself like this? I'm going off notes. I don't have this in my notes, so I just have to hope I do it right. So let's go ahead. We want to do let's say we want to do y1, y2, y10, y20, so we're doing something a little bit more interesting than y0. Y0 is kind of boring. So I want to do the integral of y10 star y20 d tau. Now this d tau is going to be really important. We've always done d tau before. I've always written d tau, and this is all space, right? Whenever I've written d tau before, I'm like, oh, it's just dx. That's not true anymore, right? We're going to multi-dimensional systems. And now this integral over all space is not just going to be negative infinity to plus infinity. It's going to have some restrictions based on how we define our theta, how we define our phi, and how we define our r. In this case, r is constant, so we don't need to worry about it. It's a constant. But we can look at the other parts. And this is going to be equal to, question mark, because I don't know, is that equal to 0? I hope it is, because these should be orthogonal wave functions. And also notice, for the 1, 0 case, the star doesn't matter. But if we did the 1, 1 case, the stars actually matter now. Taking the complex conjugates are actually going to have a really big impact on what we do. So in the past, we've been able to be a little bit lazy about that star, taking the complex conjugate. We now have to pay a lot more attention to it to make sure we're properly addressing that. So if I'm doing this integral just over 2 dimensions, I'm going to have 2 integrals. I'm going to have 3/4 pi to the 1/2 cosine theta times. Now notice, because I'm doing the 1, 0 case, there's no complex conjugate, it's a real function. 5/16 pi to the 1/2 3 cosine theta minus 1. And then I'm going to have to do, I'm going to leave space, d theta, d phi. Why did I leave space there? Something goes there, of course. So we have to remember back to something we talked about before we did this, and we said when we're dealing with spherical coordinates, our volume elements are not just dr, d theta, d phi. We've got dr, r d phi. Sorry, nope. R d theta and r sine theta d phi. If we forget that, now the r's are constants, so we're not going to worry about that part. But if we forget this sine theta, we're going to be off by a factor of pi everywhere. Pi or 2 pi. I can't remember which one it is. But we're essentially, in order to get this to be right, again, we can bring the r's out as a constant, but I should have a sine theta in there to make sure I've got my volume elements correct. Then my theta integral, I got to remember, theta is the tilt one. Theta goes from 0 to pi. And my phi is, so the way I remember is theta is tilt, phi is phase. Phi is in the xy plane, it's the phase. Theta is your tilt. So my phi is going to be from 0 to 2 pi. And I just wanted to show you this setup. Now we could bring the cosines through. We could get a cosine squared theta minus a cosine theta. We could split up the integrals. Notice the phi part, there's no phi's here, so the phi is just going to give us a 2 pi term. Question, did I forget something? Cosine squared theta, thank you. Oh, yes. Thank you, yes. Cosine squared theta. So we can bring this through, so we get a cosine cubed, and we get a minus cosine. Set that up as 2 different integrals, taking this constant factor out. And we can do this integral. We can see if we get a 0 or a non-zero value. If I didn't make any typos, and I didn't drop any negative signs, this should be a 0 integral. And we already have that expectation because these wave functions were solutions to a Hermitian operator. If these are solutions to a Hermitian operator, then all of this should be this should be an orthogonal basis set. And since we've already normalized them, this makes an orthonormal basis set. We could also show normalization by doing the same thing and asking, is it equal to 1 for two functions that are the same rather than two different functions. So we could do like a y10 star, y20, and see if the functions are normalized, and you get a probability of 1. So all of the things we've done before, we can still do. In these functions, we can plug these functions. I think I erased the Hamiltonian. We could plug these functions back into the Hamiltonian. And if we do, we will get, where's the thing like this is what we get. We will get L hat squared on our YLMs of theta and phi is equal to h bar squared L times L plus 1 y L times of L theta phi. Right? Now that's just L hat squared. This is just the momentum. This is the angular momentum squared. If we wanted to get this to be to the angular kinetic energy, we'd have a divide by 2I, right? We'd have that moment of inertia term in there as well. So if we wanted to look at that in terms of energy, we could say the Hamiltonian. Again, I erased it earlier, so I'm going to rewrite it. Sorry, I'm doing everything in blue. My other colors ran out of ink pretty much. The Hamiltonian is L hat squared on 2, oh, not 2m. L hat squared on 2I. So this is going to essentially say the energy on some y is equal to E on y. That's going to allow us to say the energy associated with this, h bar squared on 2I, L times L plus 1. And that plus 1 is actually quite interesting and quite important, but doesn't really make sense until we start looking at the other directions. Instead of just looking at the L squared, if we start looking at the other directions of momentum, of angular momentum, looking at the LZ, LX, and LY. When we start looking at those, then we start seeing, oh, it's important that we have a plus 1 there in order to satisfy uncertainty, make sure that we don't have perfect knowledge of two things that we can't have perfect knowledge of. But this is actually quite interesting. We can use this information to start looking at rotational spectroscopy. So we can look at how things rotate. We've done a couple different things now. We haven't done electronic yet. We're getting there. That's what we'll do next time. But we've looked at vibrational spectroscopy, looking at the bond moving. And this is going to be rotational spectroscopy. And it turns out that when we're looking at real atoms, it's going to be vibrational spectroscopy and rotational spectroscopy overlapped on top of each other. Because, you know, if you've got a diatomic that's spinning in space and also vibrating, you're going to have both of these things happening. We're going to look at ways that we can simplify that and separate the vibrational motion from the rotational motion, separate from the electronic energies. We're going to look at how we can split those up. It's also going to be convenient because when we look at the energy scales of those different energies, of those different spectroscopic modes, rotational versus vibrational, turns out that they're going to be off by, you know, a couple orders of magnitude. We're going to see that they fall into different parts of the electromagnetic spectrum. Vibrational is IR, rotational is microwave. Electronic, which we'll get to, is going to be in the visible. So they're going to fall in different sections of the electromagnetic spectrum because they're going to have different energies associated with them. The thing that's interesting about all of this is it really does follow, for me, is it really does follow with the parallels of what we've done before. We've got some like L squared instead of some P squared. You know, we had px squared there before. We're really doing the same type of things still. Two things I want to mention. Thing number one is this angular rotation is different than spin. Right? Angular rotation is different than spin. Angular rotation is like something that's moving around a center point. Spin is something that's rotating on its axis. And that's going to be an important distinction that we make later. But we're going to find that a lot of the operators that we use for angular momentum are going to be applicable to spin, as long as we know that we're applying them just to the spin and not to the angular momentum. This is also what's going to give rise to different kind of considerations of saying, looking at the angular momentum of the orbital versus the spin angular momentum of the electron. Right? So spin and angular momentum are going to be different things. That's thing number one. Thing number two is something that we've done in the past that I haven't explicitly said, which is how we best define our system. When we have our system defined the best way possible, we want to have as many observables described as possible. And the way that we say that in quantum mechanics is we want the maximum set of commuting operators. Right? So that's why we looked at energy and momentum, was because those two things commute. We can describe a wave function that describes both energy and momentum at the same time. For position, we had to go to average values. We couldn't get a wave function that did all three. The same thing's going to happen here, where we're going to be able to look at this total angular momentum, this L squared, and we can look at the individual components. But the question becomes, can we actually know all of the individual components? And this is where that commutator relationship that we used in the past to define uncertainty is going to come back and help us. Because essentially, what we want to find is what operators are going to commute with L squared, and then also commute with each other, so that we can know all of them using these wave functions, which I will now erase. So I've got a worksheet for us to do to look at this, but the thing, I'm just going to kind of give you some answers, and then we'll kind of look at what the consequences of these answers are. So first thing is L hat squared and LZ commute. We can know both of them. This is very interesting to prove. And when I say interesting, I mean tedious. But we can prove this. And likewise, L hat squared and Lx equals 0, and L hat squared Ly is equal to 0. So the L squared operator commutes with any one of the components, Lx, Ly, or Lz. Now the question is, does Lx commute with Ly? Because if those commute, then we could know all three angular momentum directions and the magnitude. Any guesses? Thumbs up for yes, thumbs down for no. Are they going to commute? Okay. Are you just guessing, or did you read the textbook? Option 1 is guessing. Option 2 is read the textbook. Okay, we're just guessing. Cool. So when we start looking at this, you're right. And thank you for not lying and being like, oh, no, we read. When we look at, I'm going to switch colors for this. When we look at Lx with Ly, not only do they not equal 0, but they actually They don't equal some number. They actually commute to a new operator. Yeah. Good comment. What? When I look at the commutation of Lx with Ly, I actually get Lz. Similarly, if I look at the commutation of Lz with Lx, I get Ly. And if I look at the commutator of Ly with Lz, I get Lx. And on its surface, this is really surprising and shocking. But when we think about where these operators came from, it's actually not that surprising. Right? If we think back to the cross product of R cross P, we can think about our X component crossed with our Y component gives us a Z component. Our Z component crossed with our X component gives us a Y component. Our Y component with our Z component gives us an X component. It makes sense that these would have the same type of cyclic relationship as the cross product, since that's where these operators came from. Showing this set is not so bad. It's just the chain rule 3 times. This set is actually a little bit more tricky to show. But this combination of these commutating operators and these commutating, these non-commutating operators and these commutating operators means essentially we can pick L squared and one of these 3 components. So I can't say flip back in your notes because I told you not to write it down, but which component do you want to pick? Lx, Ly, or Lz? Option 1, 2, or 3. Oh, 1. Oh. That would be tricky. So remember, the Lz component was the easiest one to write down. That was the one that was like the d by d phi squared, didn't have any cotangents or anything in it. So it turns out we always define this for our spherical system. L squared and Lz is going to be our maximum set of commuting operators. That's going to give us the most information we can know about our system if we've got a particle on a sphere. Not with restricted R, constant R, just on a sphere someplace. Now, this has a kind of interesting consequence. This means if I know my L squared, which is essentially the magnitude of my angular momentum, and I know the Lz, which is essentially the Z component of my angular momentum, that means I have uncertainty in my X and Y components. I don't really know what they are. And the way that we represent that, I'm going to venture into using orange, which sometimes is painful. But if we look at this, we've got a magnitude. That's going to be some like L times L plus 1 magnitude. And then we're going to have some Z component to it. I'm just going to call that Lz, not Lz hat. So this would be like our L squared. This would be like our Lz. This would be related to some m sub L value. But if we know those two, and I'm going to draw something in blue below it because I didn't do a good job there, what we would get is essentially some cone that this thing is processing around, where my x and y terms are unknown. If I projected this into the xy plane, I'd get some circle of possible values. It's indeterminate. I could look at averages, but I don't know eigenvalues of it. But for my magnitude in one direction and my magnitude in my Lz component, my magnitude in one direction, and my overall magnitude, those two I can define. And so when we talk about angular momentum and also when we talk about spin, we draw these conal type pictures. This cone is trying to communicate, you know L squared and Lz, but you don't know Lx and Ly, because those don't commute. questions? Okay. So this is setting us up nicely to start talking about the hydrogen atom. We are entering into phase 2 of quantum mechanics now. Or no one else calls it that, I just call it that. But essentially what we've done so far is we've solved a bunch of problems. We've said, oh, we can kind of relate these to physical systems in one way or another. But we really haven't done anything on the atomic scale. So what we'll do next time, I'm going to end a little bit early so I can talk about a couple other things when I stop the video. We've got to talk about the MATLAB assignment, and I'm also going to hand out this assignment and see if you've got questions. This is like a bonus assignment that's not worth anything, but it's still interesting. So what we're going to do next time is we're actually going to look at the Coulomb force in a three-dimensional system where r, theta, and phi can vary. Now we've already solved the phi part, and now we've also solved when theta and phi are connected to each other. So all we're going to have to do is figure out how the r part relates to it as well to get to talking about hydrogen atoms and hydrogen-like wave functions. We're good? Okay, I'm going to stop the video.